Hello, I'm Dr. Helen Findlay from Plymouth Marine Laboratory in the UK. And first of all, I'd just like to thank you for listening, but also thank AMAP for inviting me to speak to the latest science developments relating to the changing cryosphere in the Arctic. And that's what I will be talking to you briefly today, specifically looking at the impacts of that changing cryosphere on ocean acidification, sea level rise, and ocean circulation. So a lot of this information comes from the AMAP Arctic Climate Change Updates, which are available on the AMAP website, both as the full report and the summary for policymakers, but there's also some latest information that's been published this year since those reports were out. So let's begin with ocean acidification. This is my area of research, so this talk is a little bit biased towards ocean acidification. As a very quick recap, ocean acidification is where carbon dioxide is being exchanged and taken up by the ocean, exchanged between the atmosphere and the ocean, and that reacts with seawater to become part of the marine carbonate system. But if you add too much too quickly, that system becomes out of balance and it results in a decrease in pH or an increase in acidity and a decrease in carbonate ions, which results in the oceans becoming essentially more corrosive to calcium carbonate minerals. So this is latest data from our Ocean Acidification Planetary Boundaries paper, which came out in June this year, and the maps show how the surface ocean has changed in terms of acidification from pre-industrial times to present day. So the top map represents the hydrogen ion concentration, or the amount of the acidity of the ocean, and the bottom map represents the aragonite saturation state, or a level of measure of the corrosivity of the seawater to carbonate ions. And in the Arctic Ocean, you can see that since pre-industrial times, there's been about a 40% increase or more in acidity and about a 30% decrease in aragonite saturation state. And the maps clearly show that the Arctic Ocean is areas where these rates are happening most rapidly compared to the lower and mid latitudes. Now, why is that? Well, it's because of a complex connection to the cryosphere that essentially creates Arctic amplification of acidification. I'm sure many people are familiar with the idea of amplification in terms of warming in the Arctic, whereby you get feedbacks, loss of changes in albedo, etc. Acidification is essentially the same in the Arctic Ocean in that there's many feedback systems that are going on that can amplify acidification in that region. So, for example, in open ocean systems, we have sea ice loss, which means that more open water for gas exchange, more wind-driven circulation, which again can enhance gas exchange. And there's also a changing mixing regime, which can affect nutrient dynamics and the sequestering of that carbon away from the surface water down into the deep ocean. That mixing regime can also affect things like productivity, which has implications for ocean acidification as well. In the coastal systems, particularly where there are fjords and glacial inputs, then we additionally get things like glacial meltwater and sea ice meltwater, adding freshening to the system, and that causes an increase in acidification. And also we're seeing a thawing of permafrost, which is adding organic carbon and methane to the system, and thereby also increasing ocean acidification. Again, there are complex interactions there with productivity and biological aspects, but which can interact with ocean acidification as well. Ocean acidification also has consequences for organisms and ecosystems, and that's primarily why we're concerned about these chemical changes. So the AMAP report details a lot of the information about what are vulnerable species, but particularly for the Arctic, we're thinking about polar cod, Atlantic cod, northern shrimp, crabs, bivalves, and pteropods, which are particularly vulnerable. I'm not going to go into detail, but there's an example here from Nina Bednasek's group, which show that you can use pteropods, which are these small free-swimming snails with calcium carbonate shells. These pteropods actually start to dissolve in different levels of aragonite saturation state, and we can map where that severe dissolution starts to occur in the Arctic Ocean today. And you can see that we are expecting over 50% of the population of pteropods to have severe dissolution of their shells, even in today's conditions. Moving on to sea level rise, so the Arctic remains the largest regional source of global sea level rise, and that's primarily because of the Greenland ice sheet and its peripheral glaciers, which account for about half of the Arctic land ice losses and amount to roughly about a third of the global land ice contribution to sea level rise between 1979 and 2023. And again, this information is in the AMAP report. And you can see here on the left, we've got sea level rise with all the Arctic, including Alaska, contributing to nearly 35 millimeters of sea level rise. And you can see that that contribution is related to the land ice mass change moving in through that time period in the graph on the right. That's all I'm going to say about sea level rise. So moving on to ocean circulation, just wanted to highlight really that there are lots of changes. So in addition to things like the ice melt, which is contributing to sea level rise, it's also really important for thinking about ocean circulation as well. And so we've seen ice loss, but we're also seeing Arctic river discharge increasing by about 13% over that same time period. And that's important for the freshwater balance in the Arctic and beyond. So the fresh water in the Arctic comes from inflows of Pacific water, which is slightly fresher than Atlantic water, river runoff, more precipitation occurring than evaporation, and ice melt adding to the system. And then that fresh water can flow out of the system as water and ice into the Atlantic Ocean. And what we're seeing over time is that this red line here in these top graphs is the observations, while the other lines represent model representation. And the fresh water is being lost from storage as solid ice and going into liquid form as we expect as it melts. And that's just highlighted here by showing this chart of increasing river discharge through time. So the combination of increasing river discharge, increased precipitation, which again has seen about a 2 to 10% increase over that time period, and increasing ice melt is all contributing to the potential slowdown of overturning circulation. Now, this is really fundamental for how the ocean circulates around our planet, particularly at the Atlantic meridional overturning, and the meltwater forcing drives virtually all the reduction in overturning in projections to the year 2050. So in conclusion, the Arctic Ocean is continuing to acidify. That's important for how our marine life continues to survive and thrive in the Arctic Ocean, and the implications for indigenous peoples and their local communities. The cryosphere is melting, so sea ice loss, land ice loss, and permafrost thaw contribute to Arctic amplification. They also contribute to global sea level rise and also to changing ocean circulation patterns. And I would just end by saying that emissions reduction pathways are the only way to drastically slow the pace of decline. Thank you very much.